Kirchhoff's rules and complex DC circuits are going to be the topic of this lesson in my new general physics playlist, which when complete will cover a full year of university algebra-based physics. Now in this lesson we're going to find out that not all circuits can have all the resistors kind of reduced down into a single equivalent resistance. These more complex circuits, we're going to have to use what are called Kirchhoff's rules to come up with a system of equations to solve for the different currents that are flowing throughout the circuit. My name is Chad, and welcome to Chad's Prep, where my goal is to take the stress out of learning science. Now, if you're new to the channel, we've got comprehensive playlists for general chemistry, organic chemistry, general physics, and high school chemistry. And on chadsprep.com, you'll find premium master courses for the same that include study guides and a ton of practice. You'll also find comprehensive prep courses for the DAT, the MCAT, and the OAT. So we stated in the intro that some circuits are so complex that the combination of their resistors can't be reduced down into a single equivalent resistance. Well, how do you recognize that you might have one of those complex circuits? Well, the single biggest indicator is that you've got more than one battery in the circuit like this setup right here. Good chance you're going to need to use Kirchhoff's rules and set up a system of equations to solve for in such a case. All right, so Kirchhoff's got two rules. First one is the junction rule. Second one's going to be the loop rule. And the junction rule simply says that any current flowing into a junction is going to equal the current flowing out. So anything flowing in flows out, so to speak. So if I've got a junction here and I've got a junction here, maybe we deal with this one right here, and maybe current's flowing in right here, so then it's got to flow out here and here. And if I've got a total of, say, 10 amps flowing in here, then I'd have to have a total of 10 amps flowing out here and here. Or, maybe it's currents flowing in from both of these to a total of, 6 amps and 4 amps, then 10 amps here would have to flow out. But the total current flowing in equals the total current flowing out. Now here's the deal. We're going to define the current and the directions flowing, and we're going to try and do it correctly, and the directions and all, but sometimes we're going to get it wrong. Sometimes it's not intuitively obvious which way the current's flowing. What's great, though, is that if you set up the system of equations we're about to using Kirchhoff's rules correctly, the math is going to work out anyways. If you choose the wrong direction for the current, then when you solve for it, you'll end up getting a negative number. And the fact that when you solve for a current, it comes out negative, it means that if you defined it to go one way, it was really going the other way. And you just guessed wrong when you were setting up the circuits. No big deal. Kirchhoff's second rule is the loop rule, and the loop rule simply says that the voltage increases on any closed loop of a circuit are going to be perfectly matched by voltage decreases. So voltage increases, voltage decreases. When do we encounter those? Well, when you cross a battery, you're going to get either a voltage increase or decrease. If you cross it, if I define my current as going around this way, then when it crosses the battery, it's going from negative terminal to positive terminal. That corresponds to a voltage increase. But if I define my current in such a way that actually I go the other direction and I go from positive terminal to negative terminal, that's going to correspond to a voltage decrease. Now, typically when a current crosses a resistor, you're going to get a voltage decrease, a voltage drop across that resistor. Now, here's the deal. If you look at the way you've defined your current, so if you cross a resistor in the same direction as the current you've defined, that's going to be a voltage drop. So, but if you're going around a loop, and actually as you encounter that particular resistor in the loop, if you're actually encountering it in the opposite direction from the way you defined your current, then you're actually going to experience a voltage increase instead. So technically at a battery or a resistor, you could get a voltage increase or decrease depending on how you define things. Now again, normally we think of crossing a battery as a voltage increase, but again, most of the time we try to conceptually set it up to where we're going, the current is going from negative terminal to positive terminal to get that. But if you do the opposite, it would be negative instead of positive. Same thing, if I define my current right here as coming off this battery here from negative to positive and coming through this 8 ohm resistor in this direction, that's going to be a voltage drop across this resistor because I'm encountering it in the direction of my current. But let's say I decide to, make one big enclosed loop around the big loop right here. And as I go around the loop, I go around it this way. Well, the current I defined a second ago was going the opposite way. I'm just happening to go around this loop in a certain direction. It could be clockwise or counterclockwise, but once you choose your direction, you stick with it. And because I chose, in this case, counterclockwise, whereas the current in that part of the circuit was going the opposite direction, then instead of a voltage decrease for resistor, it's going to be a voltage increase instead. So, but the idea is that by the time you factor in all the batteries and all the resistors, any voltage increases are going to be perfectly matched by voltage decreases so that the overall sum is 0 between them. All right, so these are Kirchhoff's rules. So, and notice in a circuit like this, we've got a junction here and a junction here, and even though there's two junctions, we'll find out there's only going to be one junction rule because it's going to be the same sets of three currents that are flowing in and out of this junction as this one. If there were more junctions, we might end up with more than one junction rule, but it's pretty common just to have a single junction rule. But we have three different loop rules we're going to set up because we have a small loop right here, a small loop right here, and a large loop right here, giving us three possible loop rules that we could set up. So we're going to set up this system of then four equations in order to solve for some currents. So the question simply gives you this diagram here and says find the current through each of the resistors in the following diagram. So now we've got to define some currents, and again, we want to do this kind of conceptually and try and get it right, but even if we get it wrong, we'll still get it right with the math. All right, so I'm going to go start at the biggest battery I got, 20 volts, and I'm going to let him kind of govern which way the current would go. And so in this case, the current, I'm going to have it flow from negative to positive terminal flowing through here. And notice it's not just from here at the battery out, but this whole part of the circuit is one common current flowing all the way through from this junction all the way to this junction. And let's just call that I1. So we could have called it anything, but it's common to use I1, I2, I3, that sort of thing. All right, next I'm going to go to my other battery. So, and in this case, I would normally see 16 volts and be like, oh, from negative to positive, that's likely to flow this way. So, but in this case, again, from junction to junction, it's not just from here to here, it's all the way around that particular part of the loop, from this junction to this junction, and we'll call that I2. And now we can see that there's current flowing into this junction right here from both of these places. So if you decided to make the other current look like this, you would have a big problem on your hands because you'd have current flowing from three different ways into this junction and never flowing out. And so conceptually, you wouldn't want to do that. Now, again, the math might still work out, but conceptually, you definitely wouldn't want to do that. So in this case, we're going to make that right there, the current flowing the other side. And I really should, again, in similar fashion, make it throughout that whole part of the wire. And we'll call that I3. And so now we've defined the currents. Now you could have defined it any way, but you're still going to come out with three different currents you could have defined here. And which one was I1 and which one was I2 and which one was I3, you might have defined it differently. And in fact, you might have defined the directions wrong as well. Maybe you defined I1 going around this way just for the fun of it. So in all likelihood, it probably flows this way. But if it doesn't, then at the end, when I solve for I1, it'll come out negative and it'll let me know that I chose wrong. So even if you choose wrong, the math still works out in the end. All right, so now we're going to set up a system of equations. We'll start with the junction rule. If I can spell junction, that would be great. So, and the junction rule here just says pick a junction. We can pick this one or we can pick this one. So if I pick this one, I can see that I1 and I2 flow in, I3 flows out. And so the junction rule would simply say that I1 plus I2 equals I3. If you'd have picked the other junction, it would have worked the same way because now it's I3 flowing in and I1 and 2 flowing out. And you still would have ended up with I3 equaling I1 plus I2, which is mathematically the same thing we've got right here. Okay, so now we'll deal with the loop rules. And again, we've got three possible loops we can set up here. So, and in this case, I'm going to call this little one over here loop 1, this one over here loop 2, and then the big loop all the way around is going to be loop 3. So, and I can go around these loops in a clockwise fashion or a counterclockwise fashion. It's totally my call. It doesn't really matter. So, but again, I like to often try to make sense of things. And so in this little loop, loop number 1 right here, again, the current's likely in the way I've defined it to be flowing around this way. And so that's the way I'm going to go around it. And I'm going to start with the battery. So, and that battery again is a voltage increase as we go from negative to positive terminal. So that's going to be positive 20 volts. So, and then the first thing we encounter next is this resistor right here. So in that 2 ohm resistor is going to experience a voltage drop as the current goes through it. If you recall, Ohm's law says that delta V equals IR, and that's how we get the voltage drop across a resistor. And in this case, we're encountering that resistor in the same direction as the current we drew on the diagram, I3. And when that happens again, that's when you get the voltage drop. And so in this case, it's going to be I, which is I3, times R, which is 2 ohms. And so it's going to be I3 times 2 ohms, and I'm going to write that backwards. It's a voltage drop, so minus. So 2 ohms times I3, and I'm going to leave off the units here. They're all going to be in ohms. So, but I'm going to leave it off. It'll make the math a a little easier to solve for in the end if we leave those units off. Easy to get lost in the weeds with all the units on there. So next thing we're going to count on the same loop is now the 4 ohm resistor. And again, we're going to hit that 4 ohm resistor. It's current I1 that's flowing through it. And we're hitting it in the same direction as I1 travels. So it's going to be another voltage drop. And so we're going to have minus. So again, I1 times 4 ohms, which I'm going to write as minus 4 I1. And that's it. We've made a complete loop now back to the battery. And again, all the voltage increases, when added to the voltage decreases, sum to 0. That's Kirchhoff's loop rule. All right, I'm going to write this a little bit different in a little bit, but that's suffice it today. For now, that's what the loop rule is going to say. All right, loop number 2 here. And this one here, again, I'm going to start at the battery. Let's start with 16 volts. So in fact, let's just write it right beneath. So 16 volts. So next thing we're going to encounter after the battery, notice because I went from negative terminal to positive terminal, that's why I'm calling it 16 volts. In this case, I'm going around clockwise. So then we're going to hit the 8 ohm resistor, and we're going to hit it in the direction in which I2 was defined. So it's going to be a voltage drop, so we'll subtract, and it's minus 8 times I2. Carry on around this loop, and now we're going to hit the 2 ohm resistor in the same direction in which I3 is defined. So it's going to be another voltage drop, and so minus 2 times I3 equals 0. So, and notice I say equals 0 because that's the last thing we encounter before reaching the battery again in that loop. And then finally, now we've got to do the big loop. And again, once you're doing a loop, it doesn't actually matter where you start. I like starting from a battery. You could like starting from a resistor. It's your call. But you do got to do the complete loop for Kirchhoff's loop rule to apply. And so for the big loop, I'm going to start once again at the 20 volt battery. It's the biggest battery, so it's kind of the thing governing the way current flows more than anything else, so to speak. And so I'm going to do it in a counterclockwise fashion all the way around. And so first thing, it's positive 20 volts from negative to positive terminal. Next thing we're going to encounter is that 8 ohm resistor. But notice, since we're going around counterclockwise, but I2 is going in the opposite direction. And so in this case, when you encounter it in such fashion in one of your loop rules, if you're encountering it in the opposite direction in which the current's defined, instead of a voltage decrease, you're going to get a voltage increase instead. So I'm not going to subtract here. So I'm going to add 8 times I2, 8 ohms times I2. Same thing here with the battery. So when we're going to encounter this battery here, we're actually going from positive terminal to negative terminal. You only get that potential increase when you go from negative to positive. If you're going from positive to negative, you actually get a voltage decrease. So that's going to be minus 16 volts. Keep going around the loop, and now we're going to encounter the 4 ohm resistor. But we will encounter it in the direction in which the current flowing through it is defined, I1. So it will be, once again, a voltage drop. And so we're going to get minus 4 I1, and then we're back to our battery. So this all sums up to 0. So here's our system of equations. So in this case, we actually have 3 unknowns with 4 equations. With 3 unknowns, you need at least 3 equations. So apparently we've probably got a redundant equation somewhere in here. We might figure out where that is, we might not, but we've got more than enough information in order to solve this. Sometimes what they'll do to you is they'll actually come back and give you one more variable. They'll take one of these resistors or one of these voltage sources, batteries, and not give you the value for it. So that way you get 4 unknowns and 4 equations. Well, this one's going to be a little bit easier. In fact, I chose all the numbers here to make the math really nice. You're probably going to encounter some problems where the math is not so nice, FYI. Okay, so we're going to set this up just a little bit different from here. So I'm going to rewrite each one of these equations. I'm going to do a couple different things. So I'm going to move the total volts to the right-hand side of the equation. And then I'm going to try and make the total volts positive where I can, as well, as we'll see. So like this first equation here, I'm going to rewrite that. I'm going to write, so negative 2i3. So I'm going to write I1, I2, and I3 in order as well, as you'll see. So actually I'm going to start with negative 4i1. I'm going to leave a space because there's no term with I2 in it. So, and then I'm going to move on to I3. In this case, it's going to be negative 2i3. And if I subtract 20 volts from both sides, it's going to equal negative 20 volts. And I'm doing this for a reason that won't be immediately obvious, but it will be very obvious at the end of the lesson. Now, one thing to note, I would prefer to have positive 20 volts over here. So the math will work out either way. It's just my preference. And so in this case, all of these are negative. I can multiply the entire equation by negative 1, which is therefore going to make this positive 20 volts, positive 2i3, and positive 4i. And I could just erase the positive signs. They don't actually have to be there. And it's equivalent to the same equation we had just a second ago. All right, second equation here, I'm going to do the same thing. So in this case, there's no I1 term, but there's a minus 8i2. There's a minus 2i3. So, and then if I subtract 16 volts to the other side, it's going to be negative 16 volts. And we're into the same situation here. And again, I would prefer to have this being a positive number over here preferentially. So I'm going to multiply the entire equation by -1, which makes both of these positive as well. And notice I left space over here because there's no I1 term in that equation. And then finally, the last one, we've got negative 4i1. We got plus 8i2. So we've got no I3 term. And then 20 volts minus 16 volts would be 4 volts. And then subtracting over the other side would be negative 4 volts. But again, I'd prefer to have that positive if possible. So I'm going to make that positive. I multiply the whole equation by -1, which makes this positive, but it actually makes this one right here negative. Cool, and we've got 3 loop rule equations right here set up the way I want them set up. So, and then we've got this junction rule one right here, and I'm going to rewrite him as well, and we'll see why I do in just a second. Again, towards the end of the lesson, there's an easier way to solve this, as we'll see. So, but if I rewrite this one more time, the junction rule will read I1 plus I2 minus I3 is equal to 0. I just subtracted the I3 back to the other side, so again, the currents were all in exactly the same places. And ultimately what I'm setting up here is to solve this with a matrix. And even if you haven't had matrix algebra, I'm going to show you how you can take advantage of matrix algebra with your calculator to solve these. Now we're first going to solve it without matrix algebra, and then we're going to go and do it with the matrix. And you're going to be like, why don't we just do it with the matrix every time? And that's a great question. Why don't you do it with the matrix every time once you get comfortable using your calculator to do so? All right, so we've got a system of 4 equations here with 3 unknowns, and we want to solve for them. So how are we going to go about doing this? So, and again, if we're not solving this with a matrix, it turns out you've got a system of substitutions or linear combinations or something of that sort to figure this out. And in this case, no 2 of these equations have the same 2 variables so that you can reduce it down to 1 variable and solve for 1. So equation 1's got I1 and 3, the next equation's 2 and 3, 1 and 2, 1, 2, and 3, and so you have a problem here. So one thing we might do, notice this is 1 and 3 and this is 2 and 3. We might take, this is already solved for I3 on the junction rule, and substitute in I1 plus I2 right in for it. And then this first equation would only have I1 and I2. The third equation only has I1 and I2. And then we could do some sort of linear combination or substitution between those 2 to solve for it as well. So a little bit of work here to solve these. Not the easiest thing in the world, but that's the approach I'm going to take. I'm going to substitute in to that first one, in for I3, I'm going to substitute in I1 plus I2 from the junction rule. It's not the only way to solve this. There's a lot of different ways we can approach this. That's just the way I'm going to approach it. All right, so we're going to have 4I1 plus 2 times, and substitute in for, again, for I3 is going to be I1 plus I2. So, and then going back, that's going to equal 20 volts. All right, so if we expand that out just a little bit, that's going to be 4I1 plus 2I1 plus 2I2 equals 20 volts. So then I'll combine these as well and get, in fact, I'm just going to do it real quick and make that 6I1. Move that back over too. So plus 2I2 equals 20 volts. Okay, so now we've got a new equation that only has I1 and I2 in it. We had another equation back over here that only had I1 and I2 in it. I'm going to rewrite it. And so here we had 4I1 minus 8I2 equal to 4 volts. And this is a little easier to handle now because we've got the same 2 variables and 2 equations. We could do another set of substitutions if we solve one of these for I1 or I2. Or we could do my preference, which is some sort of linear combination here. So and if I take a look at these, if I want to try and make the 6I1 and the 4I1 cancel, I'm going to have to multiply both equations by some sort of factor. So, and I could do that. So, but I can see with the I2s, so this is already minus 8I2, this is 2I2, and if I take and multiply this first equation by 4, I would get plus 8I2. And then I can just simply add the 2 equations together to make that fall out. And so in this case, if I do multiply that by 4, I'm going to get 24I1 plus 8I2 equals, and 4 times 20 volts would be 80 volts. And then I'm going to combine those. And so in this case, 4I1 plus 24I1 is going to be 28I1. But notice the I2's cancel. Negative 8I2 plus I2 is 0. And then here, 4 plus 80 is 84 volts. And then I'll divide by 28. And we'll see that I1 equals, let our calculator do some work, but I chose the problem, so I know what this is going to work out to. But 84 divided by 28 is exactly 3. And in this case, that's 3 amps, or more properly, 3.0 amps with 2 sig figs. So now we know that I1 is 3 amps. And this problem just got significantly easier. Because once we know I1, we can go back to our original equations, or these versions of it right here, and plug it in for I1 here to solve for I3 here. Or plug it in for I1 here to solve for I2 here. And we'll get the other two currents in rapid succession. So one other thing to note, because having this one variable solved for makes the rest of the problem fairly straightforward, sometimes on a test, these are really long to solve for. So sometimes on a test, they'll give you either I1 or I2 or I3 so that you can actually solve it in the time allotted for the test to make it that much faster. So from here, we're going to work on getting those other two. And so in this case, if we put I1 in against 3 amps right here, we'd have 4 times 3 amps would be 12 volts. We'd subtract that from the other side. So in 20 minus 12 would be 8 volts. And so 2I3 would equal 8 volts. Divide by 2, and we'd see that I3 is going to equal 4 amps. All right, so going over to I3 is right here, and that equals 4 amps. And from here, we actually don't have to go to any other loop rules. We technically go straight to the junction rule, which again, you can think of it as a junction rule and it's just another equation. But if you understand again what it means, any current flowing in has to equal the current flowing out. Well, from this junction, there's only one current flowing out, and it's 4 amps. So far, I've got 3 amps flowing in. How much more do I need? Well, I need another 1 amp. And I2 must equal 1 amp. And again, that just flows from the equation as well. We'd have, in this case, 3 amps plus I2 equals 4 amps. I2 must equal 1 amp. Great, and now we've solved for all 3 currents. Life is good. So, and sometimes instead of simply asking for the currents, they might ask for the voltage drop across a particular resistor. Notice for the 8 ohm resistor, it's 8 times that 1 amp, and the voltage drop would be 8 volts. So if I said, what's the voltage drop across the 4 ohm resistor? Well, in this case, it's going to be 4 ohms times 3 amps. It'd be a 12 volt drop, so on and so forth. Notice we can also verify our answers and stuff like that to make sure they work. Pick a loop. If we go back to loop 1 here, 20 volt increase, followed by 4 amps times 2 ohms, 8 volt decrease, 4 ohms times 3 amps, 12 volt decrease, and an 8 volt and 12 volt decrease is a total of 20 volt decrease to match the 20 volt increase. And you could go back and verify that with any one of those loops. All right, one more thing to do here. And again, that's going back to the matrix algebra that would make this problem significantly easier than solving a system of equations with a series of substitutions. So if we go back, I wrote this in this fashion again on purpose because I'm setting the matrix up for you. So it turns out when you set a matrix up, you've got your variables, and I got I1, I2, and I3. These could be X, Y, and Z, so anything of the sort. And it's common to set it up to where you've got the variables on the left-hand side, and then any numbers with no variables, so on the right-hand side of the equation. And so in this case, we've got a matrix with 4 equations, and each of the equations is going to have 4 terms. Now you might be like, well, Chad, this one only has 3 terms. In fact, they all only have 3 terms. Well, when you've got a variable missing from an equation, you put a 0 for that entry in the matrix. So it turns out for I2 right here, I'll put it in a different color. For I2 in the first entry, I'm going to put a 0. So, but you only put the coefficient in front of the variable as well. So we're not ever going to enter I1 or I2 or I3. We're just going to put in the coefficient. 4, 0, 2, and then 20 will be the first line in our matrix. In the next one, the first term is going to be 0 because there's no I1, and then 8, 2, and 16. So in the third row of the matrix, it's going to be 4, negative 8. You got to factor in that negative. So, and then 0 for I3, and then 4. And then for the last one, it'll be 1, 1, negative 1, and 0. Well, so let's write that out again. We've got 4, 0, 2, and 20. we've got 0, 8, 2, and then 16. We've got 4, -8, 0, and 4. And I'm running out of room here. You know what? Let's just erase this and give ourselves just a little bit of room there. So, and finally, last one, 1, 1, -1, 0. And that's our matrix right there. That's what we're going to plug into our calculator. So, and you just got to know how to do just a little bit of matrix algebra with your calculator. And I'm going to use the most popular calculator out there. This one's rather old, but the TI-83 is still probably the most abundant calculator on planet Earth. So I'm going to show you how to use this to solve this matrix and solve for both I1, I2, and I3 all at the same time. All right, so here's your TI-83. I first got to turn it on, obviously. We'll clear that out. So in this case, you want to set up your matrix first. You have to define your matrix and put all the inputs in, which are right next to the calculator here on the screen. And then you've got to go back and solve it, which is straightforward in your calculator as well. Now there's a matrix button right here. I'm going to press it and it gives me some options. So and what I want to do is take one of these predefined matrices and actually edit it. So here it's just set on A by default. And I'm just going to go back in and edit A and hit enter. So, and in this case, I actually want it to have 4 rows and 4 columns. So it's going to be a 4 by 4, not a 1 by 1. All right, so now it's a 4 by 4. And then I'm going to start putting the terms in. So the first one was a 4, enter, 0, enter, 2, enter, 20, enter. We're on to row 2. 0 was the first term, enter, then 8, enter, 2, enter, 16, enter, 4, enter on the third row now, -8, enter, 0, enter, 4, enter, onto the fourth row, 1, enter, 1, enter, -1, enter, 0, enter. Now the whole thing's defined, and now we're going to quit out of there. So I'm going to hit second function and quit here. We'll get out of there. We'll go back to matrix one more time. So and now we want to do some math with that matrix. So and we want to use what's called the reduced row echelon form, RREF. So when you reduce a matrix down to its reduced row echelon form, you've effectively solved for every variable, as we'll see. I'm going to hit enter right there. So and then I want to hit the matrix button again, and I want it to do it to matrix A. So I'm going to hit enter there for matrix A. And then we just hit enter. And notice we've got 1, 0, 0, 3 for the first row, 0, 1, 0, 1, 0, 0, 1, 4, 0, 0, 0, 0. Now let's take a look at how this gives us the ultimate solution to I1, I2, and I3. So here's our matrix in reduced row echelon form. And before we go back and show you that it directly gives us the values for I1, I2, and I3, I just want to remind you what each row in the matrix originally comes from, and it's from the equation here. So here we had 4I1 plus 0I2 plus 2I3 equals 20 volts. And that's where the 4, the 0, the 2, and the 20 for that first row came from. So these represent, again, the coefficients in front of each of the variables, and this is the answer on the other side of the equal sign. And so we can see from this first one, we've got 1I1 plus 0I2 plus 0I3 equals 3. Well, effectively, that just means that 1I1 equals 3. And that's what I meant by directly, it just gives you the value of I1. The second one is 0I1 and 0I3. It's I2 equaling 1. And then the last one here is I3 equaling 4. And you see that those match perfectly the values we got. I1 was equal to 3, I2 was equal to 1, and I3 was equal to 4 right off the matrix. Now, maybe you've had a matrix algebra class and you know how to convert a matrix like this and know all the steps to get it into reduced row echelon form manually, but you don't need to. The calculator will do all the work for you. Truth be told, you don't have to have a whole lot of background in matrix algebra at all to just kind of use it the way I've shown you on your TI calculator. If you found this lesson helpful, consider giving it a like. Happy studying.